All right, buckle up, everyone, because today we are diving headfirst into one of the biggest brain-twisting topics in cosmology.
That's right. We're talking about the fine-tuning problem. Or, to put it another way, is our universe just a ridiculously lucky fluke?
We're taking a deep dive into a paper by cosmologist Sean Carroll called "In What Sense is the Early Universe Fine-Tuned?" And let me tell you, it's a wild ride.
Yeah, it really makes you question, what's normal when it comes to the universe.
Right. It's so easy to look around and think, well, this is just how things are. But when you really start digging into the physics of the early universe, whoa, boy.
That's a whole other level.
Exactly. Like, take the horizon problem, for example.
Yeah, the horizon problem, always a fun one.
It's like, imagine you're watching one of those TV shows where they have two people in different time zones, like one's in London and the other's in Tokyo, and they're trying to coordinate something.
Yeah, I've seen those.
And somehow, even though their clocks are totally off, they still manage to do the thing at the exact same time.
Right. Except instead of people and time zones, we're talking about the entire universe.
And instead of just a few hours difference, we're talking about billions of years.
Yeah, billions of years of light travel time separating different parts of the universe. But here's the thing.
What's that?
When we look at the cosmic microwave background, that faint afterglow of the Big Bang, it's incredibly uniform in temperature.
Right. It's like the universe's background noise.
Exactly. And it's the same everywhere we look, to an astonishing degree.
So the horizon problem is basically saying, how did these distant parts of the universe know to be at the same temperature if they never had a chance to talk to each other?
That's the gist of it.
Mhm.
It's like finding two cups of coffee brewed on opposite sides of the planet that are somehow the exact same temperature.
Right. You'd think that given enough time, everything would just kind of even out, right?
That's the intuition. Like, if you stir those two cups of coffee together, eventually they'll reach the same temperature.
Yeah, it all mixes together.
But with the universe, it's not that simple. Because gravity, the force that brings everything together, doesn't work that way on cosmic scales.
Oh, really? How so?
It's counterintuitive, but if gravity had unlimited time to work its magic, the universe would actually become more clumpy and uneven, not less.
Wait, hold on. So you're saying that gravity, the thing that makes stars and planets clump together, would make the early universe more chaotic if it had more time?
Exactly. It's all about how gravity amplifies differences over incredibly long periods. Imagine a perfectly smooth sandbox.
Okay, good sandbox.
Now, if you leave that sandbox out in the wind and rain for millions of years, what do you think will happen?
I'm guessing it won't stay smooth
Right. You'll get hills and valleys carved out by the elements.
because the wind and rain will push the sand around.
Precisely. And in a similar way, gravity, given enough time, would amplify any tiny differences in the early universe, making things less uniform, not more.
So the real puzzle isn't why those distant parts of the universe look so similar. It's why they haven't completely gone their separate ways and become a cosmic mess.
You got it. And to understand that, we need to shift our perspective a bit.
Oh, I love a good perspective shift. Lay it on me.
Instead of thinking of the universe as a single snapshot in time, imagine it as a vast collection of all possible cosmic movies.
Okay, I'm visualizing these cosmic movies. Go on.
And each movie represents a different way the universe could have evolved from its initial state.
So, like, some movies are blockbuster hits and some are total flops.
Exactly. And the question becomes, which of these movies are the most likely to play out according to the laws of physics, particularly gravity?
So we need a way to figure out which cosmic movies are the most plausible.
Exactly. And that's where the Gibbons-Hawking-Stewart measure, or GHS measure for short, comes in.
The GHS measure. Sounds important.
It is. Think of it like a cosmic recipe book.
Okay, I like where this is going. A cosmic recipe book.
It tells us which ingredients, or in this case, which initial conditions, are most likely to bake a universe that looks like ours.
So it helps us figure out which cosmic movies are the blockbusters and which ones are destined for the bargain bin.
You got it.
So we've got this cosmic recipe book, this GHS measure, and it's telling us which universes are the most likely, the blockbusters, based on how gravity works. But does it actually help us understand, the universe we live in?
It does. In fact, it completely changes how we think about some of the so-called fine-tuning problems, like take the flatness of the universe.
Yeah, the universe being flat, not curved like a Pringle chip.
Right. It's mind-bogglingly flat, which means it had to be even flatter in the very beginning.
And the odds of that happening by chance, it's like winning the cosmic lottery a gazillion times in a row.
That's what we used to think. But the GHS measure throws a curveball at that whole idea.
Oh, tell me more. How does it do that?
Well, it turns out that according to the GHS measure, flat universes aren't actually all that unusual.
Wait, really?
Yeah, they're practically the norm. It's like flipping a coin a million times and getting heads almost every time.
But that's not how coin flips usually work.
Right. But with gravity and the way it shapes the universe, those flat universes, they're like the heads in our cosmic coin toss. They're just naturally more likely.
Okay, so the flatness problem, which seemed like this huge mystery, it might not actually be a problem at all.
Exactly. Our intuition about what's fine-tuned was a bit off.
Gravity's got our back, basically.
You could say that. But of course, there's another biggie we have to address.
Oh yeah, the smoothness problem. Even if the universe is flat, it's still incredibly smooth. The cosmic microwave background, that afterglow of the Big Bang, it's unbelievably uniform in temperature.
And that's where things get really interesting.
Meaning?
Meaning, while the GHS measure says flat universes are common, a universe as smooth as ours
Mm.
is a whole different story.
How different are we talking?
Think one in a Googleplex.
A Googleplex.
A Googleplex. It makes a trillion look like a grain of sand in the Sahara.
Okay, so smooth universes are rare, super rare, but why is that a problem?
Because it means our current understanding might be missing a piece. We have inflation, which helps explain how distant parts of the universe could have similar temperatures.
Right, inflation. The universe suddenly went through this crazy growth spurt right after the Big Bang.
Exactly. But think of inflation like having this perfectly level runway for an airplane to take off from.
Okay, I can picture that.
It's great once you're in the air, but you need those perfect conditions on the ground first.
So you're saying that for inflation to even happen, you need very specific conditions.
Yes. And those conditions, well, those might be the real fine-tuning problem.
So it's like needing a perfectly balanced house of cards just to get the rocket off the ground.
That's a great way to put it.
Okay, so where does this leave us? We've got this universe, amazingly flat thanks to gravity doing its thing over billions of years. But then there's the smoothness, this cosmic microwave background that's just, well, unbelievably uniform. What's the takeaway here?
The big takeaway is that while we've made progress, there's still a huge mystery at the heart of cosmology. Why is our universe the way it is?
It's like we've got this amazing puzzle, and we've put together a few pieces, but the picture is far from complete.
Exactly. And those missing pieces, they might point to something truly fundamental, something beyond our current understanding of physics.
Like what? Give me some possibilities.
Well, for one, there might be something happening in the very, very early universe, even before inflation, that we just don't know about yet.
So like a pre-inflation era, a whole other chapter in the universe's story that we haven't even begun to imagine.
Exactly. Or maybe, and this is even more radical, maybe it's not the universe that's the problem, but our way of thinking about it.
Whoa, okay, now you're really blowing my mind. What do you mean by that?
Well, we tend to think of the universe as this incredibly full place.
Yeah, stars, galaxies, planets, black holes, the works.
Right, all packed in there.
Huh.
But what if? What if that's not actually the case?
Okay, I'm intrigued. What if it's not the case? What are you suggesting?
What if the universe is actually mostly empty?
Mostly empty.
Yeah, like a vast, expanding void with just these tiny pockets of matter scattered here and there.
So instead of a cosmic pizza with everything on it, it's more like a plain cheese pizza with just a few scattered toppings.
That's a surprisingly accurate analogy. And if that's the case, then maybe, just maybe, those incredibly small odds of our existence, that one in a Googleplex, maybe those odds aren't so crazy after all.
So if we change our assumptions about what the universe is supposed to be like, suddenly things don't seem so fine-tuned?
It's a possibility, isn't it? Maybe we're limiting ourselves by sticking to this idea of a universe that's chock full of stuff.
Because our little corner of the universe might be the exception, not the rule.
Exactly. And that's the beauty of cosmology, isn't it? We're constantly challenging our assumptions, pushing the boundaries of what we thought we knew.
And sometimes those assumptions lead to dead ends, and we have to be brave enough to turn around and explore a different path.
Precisely.
Well, that about wraps up our deep dive into the fine-tuning problem. We've covered a lot of ground, from the horizon problem to the cosmic microwave background, and even questioned the very nature of the universe itself.
And just remember, this is just the beginning. There are so many more mysteries out there waiting to be explored.
So keep those telescopes polished, those imaginations firing, and maybe, just maybe, one of you listening will be the one to finally crack the code of the cosmos. Until next time, keep looking up.